Yeah. See if this is going to work. Yeah, we need the new battery here. Is it time to start the class?
Yeah.
Is there anybody in the room? So you can, yeah, you can. Disciplines, nobody. Wow. It's the first time not people on Zoom.
Mm-hmm.
At least the first time this semester, but well, hopefully people that were supposed to be online, that registered online, are in person here.
One guy showed.
Oh, well, okay. Who is that? Okay. Tyrell, okay. We are going to finish chapter 21. It is relatively short and easy chapter, but it has two points that we have to learn very well. The right-hand rule. The formulas are always provided, but the right-hand rule cannot be provided. Right? You just have to learn how to use it. So last time we started with talking about the fact that magnetic charges do not exist. Magnetic monopoles do not exist. This means that magnetic charges always go, well, but not exactly charges, but magnetic poles always go north and south next to each other, on top of each other in a sense. And if you think about the North Pole as a plus and the South Pole as a minus, they cancel out each other since they're almost on top of each other. And the result is that anywhere around us, the net magnetic charge is equal to 0, because always you have plus and minus on top of each other, north and south pole on top of each other. So this means that you recall from chapter 18, Gauss's law, the first Maxwell equation, which says that the electric flux going through any closed surface is equal to the total electric charge inside that surface, inside the volume defined by that surface, divided by electric permittivity, fixed number. So this is Gauss's law, the first Maxwell equation. The second Maxwell equation, in a similar manner, you can either formulate as no magnetic monopoles exist in nature, or alternatively, you can write in a manner similar to Gauss's law. You can say that the magnetic flux going through arbitrary closed surface is equal to 0. Well, strictly speaking, if magnetic monopoles existed, you can write total magnetic charge, total divided by certain constant. But since magnetic charges do not exist, they're always plus and minus together, cancel out each other. This means that the magnetic flux through arbitrary closed surface is equal to 0. So this is the second Maxwell equation. And on Friday, we're going to write the third Maxwell equation. And next week, the fourth Maxwell equation. And then we're going to have a full handle on all electromagnetic phenomena. So all electronics and everything else around us is going to be an open book, let's say, if you know how to read it. Okay, so last time we talked about the way we detect the presence of magnetic fields, or our definition for magnetic field. The definition for magnetic field was done using the fact that moving electric charges that are moving in some magnetic field are going to experience a force, magnetic force. And we said that the experiment shows that the magnetic force that acts on a charge with magnitude Q, velocity magnitude V, in magnetic field with strength B is given with this expression, the product of magnitude of charge, magnitude of velocity, magnitude of magnetic field times sine of the angle, theta, between the velocity vector and the magnetic field vector. So this is the Lorentz equation, and it is, we can consider this equation as our definition for magnetic fields. It is more complicated definition than electric field. And again, the reason for this complication is due to the fact that no magnetic monopoles exist. So if you recall, the definition for electric field was like this. Electric field is force per unit charge. But since we don't have magnetic charges, we cannot use this simple definition. Instead, we use some complicated, relatively complicated observation, which is the fact that electric charges in magnetic field, if they're in motion, they're going to feel a force of this type. We said that the direction of the magnetic force that acts on a moving electric charge is given with the first right-hand rule. So you have to add right-hand rule number 1 in order to have a more complete description of the interaction between the force, between the magnetic field and the electric charges. So this right-hand rule applied correctly tells you that the magnetic force is perpendicular to the velocity of your moving charge, 90 degrees always between them. And also the magnetic force is also perpendicular to the magnetic field B. The first fact that the magnetic force is perpendicular to the velocity vector implies that the work done by magnetic forces on electric charges is 0. The work of the magnetic forces on charges, on electric charges, is 0. So look, if you have, let's say, magnetic field into the board, let's say, here, into the board magnetic field everywhere. This is magnetic field B into the board, right? This is the sign for into the board field. And well, it is the same everywhere here, into the board. And let's say that you have a positive electric charge, like this one right here, moving in this direction, B. The first right-hand rule says that thumb in direction of the velocity vector, fingers in direction of the magnetic field. This means that the magnetic force acting on this charge is this way, is the direction of the magnetic force. Well, last time we established that this electric charge under influence of magnetic force is going to start moving along a circular part of a circle, or it may even complete a full circle if it doesn't get out of the magnetic field. So the trajectory of this electric charge is going to be a circle. But this force, this magnetic force, changes the direction of motion, curves the trajectory of the charge, but it doesn't change the magnitude of velocity because it doesn't do work on these charges. So magnetic forces do not do work, and this is a typical question in different forms that you can encounter in quizzes and standardized tests. Okay, now look, if you have a moving charge, electric charge, well, we brought the force that acts on this moving charge. What if you have a stream of electric charges in motion? What do you call a stream of electric charges in motion? You call them electric current. So since each of the charges is going to feel this magnetic force, the entire stream of charges is also has to feel electric force, magnetic force of this type. And you have, of course, so this means that if you have, here is the same magnetic field into the board, and let's say that here is a piece of wire with current that flows in this direction, current I that flows in this direction. Exactly the same right-hand rule tells you that this piece of wire is going to, with current in it, is going to feel a magnetic force, again given with the right-hand rule. So this piece of wire is going to feel magnetic force this way. Well, it is not that difficult to figure out the magnitude of this magnetic force. So if this piece of wire, with current has a length L, length of the wire, this piece of wire with current. Sorry for this is terrible. Oh, maybe. So if the length of this piece of wire is L, of course, this means that, well, this piece of wire has to, in order to make the current flowing, you have to connect it to some battery like this. But we're only talking about this piece of the circuit that is in magnetic field. The rest may be out of the magnetic field, so you don't worry about it. So look what happens. Each charge that is located in this piece of metal with current is moving, and you have a magnetic force of this type acting on this electric charge. And look, you can say that the magnetic force is going to be charge. So the velocity of your moving charges in this piece of wire, you can write as Well, the distance, velocity is distance divided by time, displacement divided by time. If you take the time interval to be the time interval necessary for the positive charge to cross this entire length L, you can write the magnitude of velocity V, you can write it as the distance L divided by the time interval T needed to cover this entire length. The rest stays unchanged, the magnitude of velocity and sine of the angle between the velocity vector and the magnetic field. And now, instead of dividing the length to the time interval, you can divide the amount of charge to the time interval. But the amount of charge divided by time interval gives you exactly the magnitude of the current that is flowing in this piece of wire. So this in the oval, this expression is exactly the current. And as a result, you have that the magnetic force acting on your piece of wire with length L is equal to the current times the length of the straight piece of wire in magnetic field times magnetic field times sine of the angle. Now, the angle is the angle between the magnetic field vector and the current, but the current is flowing in direction defined by the length of your piece of wire, right? The angle theta is defined by current, and the current is along the direction of the wire, this way or in other direction, in opposite direction. It's always going to give you the same result. So next time we're going to see a demonstration. We're going to place a piece of metal in magnetic field, and we're going to drive current through this piece of metal, and you're going to see how this piece of metal, under influence of a force like this, is going to start moving. So we're going to set up this for well, in general, you need quite a strong current. So it is not that trivial to set it up, but it is not complicated either. So we're going to see it next time. Okay, any remarks? Yeah.
Going back to the diagram, if you were to have like an infinitely large magnetic field, would it complete a full circle, or what would happen to that?
So what would happen if you have infinitely large magnetic field and you have a current? So the entire circuit here, electrical circuit, is in magnetic field. Is this what you're saying? Well, let's see. This is exactly what we want to see now. So here is very long, very big area covered with magnetic field. So we need a two-dimensional. So think about this diagram this way. Maybe here is one end. Here is of the current, metal, piece of metal with current, with length L here maybe. And you have to close the circuit like this. So this is, maybe this is getting in. Here is a rectangular piece of wire with current in it. I can make the current maybe by placing a battery here. Which way to drive it? Let's drive it this way. So I can place a battery like here and here, yes. And this is what you were asking. So the area occupied by magnetic field is so big that the entire electric circuit is in that magnetic field. Let's see what's going to happen in that case. Well, let's remove this battery so it not to obstruct our diagram. We established that this piece of straight wire L with length L is going to feel a force this way. Right? Remember, the current is flowing this way. The current is flowing this way. This. Well, if the current is flowing this way on this side, it is going to be flowing this way on this side. It is going to flow this way here and this way here, so that it goes around in this way. So this is the magnetic force on this piece. Let's determine the magnetic force that acts on the other side. Well, current this way, magnetic field this way, you're going to have this force vector in this direction. So I'm trying to do a three-dimensional drawing. It is not that easy, but imagine that this is like this rectangular frame is oriented the way I have tried to draw it on the diagram. Now, what would be the direction of the force that acts on the side, on this side here? Well, here on this side, you're going to have force this way, and on this side, you're going to have force this way. So the forces on this and this side, kind of, they're trying to squeeze the frame. If the frame is strong enough, it is not going to move. Those two forces are not going to do anything. But the other two forces, if you place an axis of rotation here so this rectangle can spin, are going to make this rectangular frame spin this way. So if this side of the rectangle is omega, let's say, or not omega, let's make it W lowercase. You can calculate the torque generated by this and this force. So you have a pair of forces that are trying to rotate this frame. The lever arm is going to be the product of the force times this length. And the resulting torque, after you take into account that you have two sides with forces on them, the resulting torque is going to look like this. Current that flows multiplied by this length of the rectangle multiplied by the other length of the other side of the rectangle, multiplied by the magnetic field, and multiplied, well, that's pretty much it. Now, the product of the two sides of the rectangle give you exactly the area of this rectangle. In other words, the torque is going to be current times the area of the rectangle times the magnetic field. And now look, when this frame, this rectangular frame turns around, as it turns, the lever arm of the force F is going to drop. And you can, if you draw carefully the diagram, you can see that the lever arm is going to drop by a factor of sine of an angle phi, where the angle phi is defined as the angle between the normal to the area. So the normal right here to this area and the magnetic field lines. So the normal is this way, the magnetic field line is into the board. So you have to figure out that angle. In general, this is the general expression for the torque. And this torque is going to start spinning this frame. Well, when this frame reaches certain orientation, the angle here is going to become either 0 or 180 and the torque is going to be 0. But since this frame is spinning, it is going to continue spinning because of inertia. And if at that moment you switch the direction of the current, the torque again is going to keep rotating again. So you have to switch the direction of the current every twice per cycle in order to have a continuous rotation. Yes.
I'm kind of confused on how you use the right-hand rule with the current on the right and the left sides, because like on the right side, isn't the current going the same direction as the magnetic field? So how would that make?
On which side? Here?
No, on the
Here.
right, yeah, that side.
Well, it is, look, I'm trying to show three-dimensional diagram, but in general, when this frame is oriented in such a way that you just see this and this end, let's say a cross section right here, right? You have, if I draw the same diagram in cross section like this. So here is the same diagram, magnetic field everywhere magnetic field, the same magnetic field. But now if I draw only a cross section of this frame like this, cut right here. So you're going to see that on this side, the current gets out of the board. On this side, the current gets into the board. But those are the currents on those sides right here. And the angle between the current on this side and the magnetic field is 0. Sine of 0 is going to be 0. So no magnetic force on this side. But that's fine. In a similar manner, no magnetic field on this side. But the magnetic field still is going to act on this side and the opposite side of the rectangle, and you're going to get this rotation. So the rotation is going to be like this. Yeah.
So the rectangle is three-dimensional. Is the magnetic field also three-dimensional, or is the magnetic field?
Well, again, my artistic abilities are really very limited. So next time I'll prepare slides that show.
But in this example, is your electric field three-dimensional or is it two-dimensional?
Well, the magnetic field is into the board. So into the board, and the frame is partially rotated. When the frame is like this, so the current on the front side is flowing this way. On that side, you have the force this way. Magnetic force this way. The other side, the magnetic force, the other side that is behind here of the rectangle, the force is in opposite direction. And you have this rotational motion of the frame. And this is exactly, what is it? It is exactly electric motor. So again, this magnetic field is going to rotate the frame. But when it rotates to when it rotates to 90 degrees, you're going to see that this angle is going to be either 0 or 180, and the torque is going to be 0. And you have to continue rotating for a short period of time by inertia. And at the moment when it passes through the 0 angle, let's say, you have to switch the direction of the current in order to continue a torque rotating the same way. And in electric motors, this is done with brushes, with the brushes that you may have seen if you have opened an electric motor. For our case, I can demonstrate how it works with this. Here's a battery. There is a small magnet that is going to create the magnetic field. And here is the frame. Instead of rectangular shape, it is easier to make kind of circular shape. And here it is. If you, well, you have to get it going. But if you're lucky and if you play enough with this and make sure that the battery is fresh, you're going to make it rotate. You can play around with this. And this is the simplest electric motor that you can create. Again, the battery is not very fresh, but I can bring another battery and you guys put together exactly the same setup, and you're going to see that it works exactly like electric motor. So what happens very often, people short the circuit and the battery gets worn out very quickly and it stops working. But here it is. Okay, next time I'll get a fresh battery and you're going to see that how simple electric motor is like this. It's not much different from this. Okay. Any remarks and issues? Okay, so this chapter has two quite separate topics. The first topic is motion of charges in magnetic field, or currents in magnetic field, which is pretty much the same. And this is what we got now. The second part is clarification of what we said before. Before we said that magnetic monopoles don't exist, and all magnetic fields are created by currents, electric currents. Either atomic size electric currents, or maybe subatomic size electric currents, or maybe electric currents created by in a piece of wire. So the second part of this chapter is a description of magnetic field created by a current that flows either along a straight piece of wire or along some other shapes that are easier to analyze. So we start with the magnetic field created by current that flows along a straight piece of wire. Let's say you have a current like this, and here is the current flowing in this very long and straight piece of wire. What is the magnetic field created by this moving, by this current? Well, if this piece of wire is almost infinitely long, it is clear that the magnetic field close to the current is going to be stronger. Right? You're closer to the source, you better have a stronger magnetic field closer to the source. And you can demonstrate that the magnetic field created by this current in this long piece of wire is given with the following expression. E is equal to it is proportional to the magnitude of the current, inversely proportional to the distance from the current. So the farther away you go, the magnetic field gets weaker. There is a coefficient of 2 pi in the denominator. And there is another coefficient describing the magnetic properties of the medium around this current. If the medium is vacuum or air, the coefficient of proportionality mu naught, called magnetic permeability of vacuum, has a numerical value 4 pi 10 to the negative 7, appropriate SI units. Now, what are the appropriate units? So magnetic field is measured in Tesla. Electric currents are measured in amperes. So mu and distance, of course, the distance r is measured in meters. So the SI units for magnetic permeability of air or vacuum is going to be Tesla multiplied by meter and divided by ampere. Want the units, SI units for magnetic permeability of vacuum. Okay, but magnetic field, just like electric field, is a vector. What is the direction of the magnetic field, let's say, at this point in space? What is the direction of the magnetic field created by this current at that spot? The direction we're going to describe with another second right-hand rule. So this formula has to be supplemented by a second right-hand rule. And this second right-hand rule says this: the thumb of your right hand should point in the direction of the current. And in that case, your fingers going around the current are going to point in direction of the magnetic field lines. So the magnetic field lines are going to be like circles around the current. Circles like this, with orientation given with the direction of your fingers. So magnetic field is going to be this way, and on the other side, it is going to be this way, like this. In other words, on this point, the magnetic field is going to be into the board, while on this side, the magnetic field is going to get out of the board. Again, two-dimensional thinking is needed here in order to visualize. Magnetic field lines are like rings, like circles around the current. Well, the magnetic field lines, let's say farther away, are going to be, again, this way, into and out on the side. Yes, pencil. So currents flowing along a straight pieces of wire are everywhere around us. So here, behind the wall, you have some current flowing and feeding the lights. So at any moment, we have a magnetic field created by this current. Well, luckily for us, even if you get close to this current, magnetic permeability is a relatively small number, which makes the magnetic field around the current flowing here in the wall relatively small, and you don't feel it. On top of that, the direction of the current oscillates 60 times per second, which makes the magnetic field oscillating 60 times per second in its direction. And the result is you just don't feel it. But if you have a permanent current, DC current, direct current, that is strong enough, that DC current is going to generate magnetic field that you're going to be able to easily detect, either with a compass or with other tools. Okay, any remarks so far? Anything? Okay, so on Friday, I'll give a general formula that you can use to show, to calculate the magnetic field created by arbitrary shaped current that is flowing in a wire with arbitrary shape. But that formula is going to be quite ugly, and you're probably not going to use it. Yes.
So if I'm understanding this correctly, the first equation we used for the magnetic field and the right-hand rule number one is for a charge moving, but this is for a current. Is that the difference between the two? Or-
So the first right-hand rule describes the direction of the force acting on a moving charge or current. The second right-hand rule describes the direction of the magnetic field, invisible thing, right? This is what makes the material more abstract and difficult. You can see the force in a sense, but the direction of the magnetic field is our imagination.
So this would be the same if it was a charge moving upwards with a velocity, you still use right-hand rule number two. It doesn't have to be current.
So the second right-hand rule describes direction of magnetic field. The first right-hand rule describes direction of force that acts on a charge.
But for the second, for this one with that equation that you wrote on the top right-hand corner, it only works with current, it doesn't work with charges moving.
Well, currents are made of moving charges. The formula for magnetic field created by a single point-like moving charge is quite complicated, and we don't deal with it. This is a stream of moving charges, and they create magnetic field in this with this orientation. So it is well. The first right-hand rule, you already have some magnetic field created by some other means, permanent magnets or other currents. And you have a charge or a current in this previously created magnetic field. And you want to figure out the direction of the force that acts on your moving charge or current. Here, you are told how to create magnetic field, right? Here, the magnetic field was created for us by some other means that we don't think about. Here is how we create the magnetic fields. Okay, but good question, and you must keep asking million questions like this. At the moment when you are able to formulate the question, half of your job is done, or more than half, because you can always find somebody to answer the question. The difficulty is to formulate a question, not just feel confused. You have to try to figure out the source of confusion, and then we can discuss and we try to figure out what's happening. Okay, any other remarks? Okay, the next easy to write magnetic field would be a magnetic field generated by a current that flows in a circular loop. So here it is a circular piece of wire. And let's say that the current is flowing this way in this circular piece of wire. And you have some battery hidden here that moves the current in this direction. The formula describing the magnetic field created by this circular loop current is really very ugly. At different points, the formula is very complicated, and we're not going to write it. But at some particular point, it is a simple formula. Right here in the middle of the circular loop, the magnetic field is given by mu0 times I divided by 2 times the radius r of the loop. But only at this point, only at the center. Anywhere else, the magnetic field here, very difficult to write down. Magnetic field here, very difficult to write it down. But at this particular point at the center of the loop, formula is simple and given this way. The direction of this magnetic field again is with the second right-hand rule. Now you have to place your hand this way, like here. Here is the thumb along the direction of the current, and your fingers again form circles that indicate the direction of the magnetic field. On this side of the loop, the magnetic field is going to be into the board. So here it is into the board magnetic field, while on the other side, the magnetic field is out of the loop, just like the second right-hand rule describes. So you may say, well, why do we need to write a formula for magnetic field that has a strength that we can only write for this particular point and not at any other point? In other points, it is very complicated formula. Well, the reason for that is that when you put many rings next to each other, so multiple rings like this, imagine a ring and next to it another one, you form a cylinder with multiple rings with current in there. Or if you look at this from the side, this is going to look like this here. It is multiple rings in a spiral shape. And you can create the current right here. This is a shape of current called solenoid. And you can prove that all those circular rings, they reinforce each other's magnetic field, and the total magnetic field in the inside of the solenoid right here is given with, what is it, mu naught times the number of rings per unit length times the current. So n here is number of loops per unit length. This is the length of the solenoid L. So number of loops per unit length. And look, this formula now is valid for the magnetic field everywhere inside the solenoid, not just in the axial point. Any point that is inside the solenoid has this magnetic field. The direction of that magnetic field again is described with the second right-hand rule. So you have to place again your right hand, the thumb in direction of the current. So let's say if the current is flowing, well, again, three-dimensional thinking here, I'm giving up to try to describe it, but you have to use your imagination to figure out. The magnetic field lines are going to be like this, either in this direction or in opposite direction, depending upon how you imagine the orientation of the current and the solenoid. So the solenoid is the standard device to create constant magnetic field inside the solenoid. And by the way, you can demonstrate that outside the solenoid, the magnetic field is practically zero. Okay, so we're going to stop at this time. And what is left for Friday is, of course, homework questions. I have multiple quiz questions for you for this chapter, most of them related with the right-hand rule, the first one or the second one. And the last thing that is left from this chapter is to write a formula that allows you to calculate theoretically the magnetic field created by a current that flows in along an arbitrary shaped circuit. Not just along a circle or along a straight line, but some arbitrary shape of your choice. So this is going to be for next time. Look at the homework assignment. We want to finish this homework assignment on Friday by midnight.